Have you ever tried to find one specific grain of sand on a beach? I mean, it sounds impossible, right? Well, that's pretty much the kind of challenge we're giving to artificial intelligence every single day. In this explainer, we're going to dig into exactly how AI gets fine-tuned to solve these crazy needle-in-a-haystack problems. And our guide? The high-stakes world of credit card fraud.
Okay, so this slide gets right to the heart of it. What you're looking at is a visual of real-world credit card data, and it's wild. A huge 97.7% of all transactions are totally legit. That leaves this tiny sliver, just 2.3%, that's actual fraud. In data science, this is called a severely imbalanced data set, and it's exactly what makes spotting the bad guys automatically so incredibly hard. So yeah, let's officially frame this. We are looking at a classic needle-in-a-haystack problem. The challenge of sifting through millions of normal, everyday purchases to find those few fraudulent ones, that's not just a headache for banks, it's a really fascinating puzzle for data science. To really get a sense of the scale here, look at these numbers. The actual data set the researchers worked with had almost 95,000 transactions, and out of all of those, just over 2,000 were fraudulent. The AI's job is to learn how to spot those super rare events in a massive sea of completely normal activity.
Now here's a brain bender for you. What if an AI model did nothing? What if it just guessed not fraud every single time? Well, technically, it would be right 97.7% of the time. That accuracy looks amazing on paper, right? But in the real world, it's completely useless because it would miss every single fraudulent charge. So the real question is, how do we build a model that's actually smart enough to find that tiny 2.3%?
So how do you even begin to solve a problem like this? Well, the researchers turned to a really powerful and popular tool in machine learning called a random forest. Let's break down what that actually is. Okay, so a random forest, what is that? The simplest way to think about it is that it's an ensemble method. That just means instead of relying on one single know-it-all model to make a decision, it builds a whole team, a big collection of individual decision trees, and then it uses their collective wisdom.
You know, the best analogy is to think of it like a committee of experts. Each tree in this forest is like a specialist who looks at the data from a slightly different angle. So when a new transaction comes in, all the trees cast a vote, fraud or not fraud, and the final decision? It's just whatever the majority voted for. This teamwork approach makes the whole model way more robust and accurate than any single tree could be on its own.
But here is the absolute key. Just having a powerful algorithm like a random forest is only the beginning. It's not some magic box you just turn on. To really unlock its potential, you have to tune it. You have to carefully adjust all its little settings to make it work perfectly for this specific problem of finding fraud. And those settings, they have a name: hyperparameters. Honestly, the best way to picture them is as the dials and knobs on the machine. These are the things the data scientist has to set before the model even starts learning. They control the fundamental way the algorithm is going to behave. The entire process of tuning is basically a search for that Goldilocks zone. You don't want your model to be too simple because then it'll miss the important patterns, but you also don't want it to be too complex because then it'll just get confused by all the random noise in the data. You're searching for that setting that is just right. And this slide really nails that balancing act. If your settings are too simple, the model underfits. It basically draws a really crude line and misses all the nuance. But if your settings are too complex, it overfits. It literally memorizes the training data, warts and all. And that means the second it sees a new transaction it's never seen before, it's going to fail miserably.
Let's make this a little more concrete. A perfect example of one of these dials is a parameter called max depth. This literally tells each decision tree in your forest how deep it's allowed to grow. By putting a limit on that depth, you're directly stopping it from getting way too complicated and overfitting the data.
And max depth is just one of the knobs you can turn. There's n estimators, which is just how many trees are in your forest. There's min sample split, which tells a tree when it's allowed to create a new branch. And max features, which limits how much information each tree gets to see at once. Every single one of these helps fine-tune that delicate balance between learning the important stuff and just ignoring the noise.
Okay, so that's all the theory. Let's pivot back to the real world and see exactly how the researchers put all these ideas to work to hunt down those fraudulent transactions.
So, before they could even think about tuning, they had to deal with that huge data imbalance we talked about. They used this really clever technique called smoot,
What Smote does, basically, is it looks at the few examples of fraud that it has and it intelligently creates new, totally believable, synthetic examples of fraud. It's like giving the AI a bunch more needles to study, so it gets way better at recognizing what a needle looks like in the first place.
So their whole process was just super logical. First step, prepare the data. They used Smote to turn that lopsided 97-2 dataset into a perfectly balanced 50-50 split. Step 2, build the initial random forest model. Then came the most crucial part, step 3. Perform that hyperparameter tuning, systematically trying out different combinations of all those knobs and dials. And finally, they unleashed their fully tuned model on data it had never seen before to see how well it really did its job.
So, after all that meticulous preparation and all that careful tuning, did it actually work? Well, let's take a look at the results, because they're pretty impressive.
What you're looking at here is called a confusion matrix. Think of it as the model's final report card. The diagonal line, from top left to bottom right, that's all the correct predictions. We're talking over 83,000 legitimate transactions and 87,000 fraudulent ones all identified correctly. The other two boxes, those are the mistakes, the false alarms, and the frauds it missed. And as you can see, those numbers are tiny in comparison.
So what did all of that add up to? A final accuracy of 98%. But even more importantly, the researchers looked at something called an F1 score, which is super important for these imbalanced problems, and that score was also 98%. I mean, that is a phenomenal result. They went from a dumb model that was 97.7% accurate but totally useless to a smart tuned model that's 98% accurate and incredibly effective.
And here is the final proof. This is called an ROC curve. Now, all you really need to know is that a perfect model would have a line that shoots straight up the left side and then straight across the top. As you can see, this model's curve gets incredibly close to perfect, with a final score of 0.98 out of 1. This just confirms that the model is exceptionally good at telling the difference between a real purchase and a fake one.
So what's the big takeaway from all this? Well, it really boils down to 3 key things. First, picking a powerful algorithm is just the starting line. Second, for these needle-in-a-haystack problems, you have to fix the data first, using clever techniques like Smote. And finally, it's that careful, deliberate tuning of those dials and knobs that turns a pretty good model into a great one that actually has a real-world impact.
And that leaves us with one final exciting thought. We've just seen how this combo of smart data prep and fine-tuning can find financial criminals. But what about other haystack problems? You know, like discovering a rare disease from medical scans, or finding a new planet in telescope data, or identifying a critical cyber threat? The real question is, how else can we take this powerful approach and use it to solve some of our biggest challenges?